The question 2.50. The longest wavelength doublet absorption transition is observed at 589 and 589.6 nanometer. Calculate the frequency of each transition and energy difference between the two excited states.
Ma'am, so the formula should be nu equals C by lambda. Yes, ma'am, I'll just do the
That's all.
calculation.
Then what do you do? Then from there you can calculate the
Nu1 minus nu2.
it's all.
Yes, ma'am.
See, the longest wavelength doublet. Forget about all these stories. You don't mind about this. The longest wavelength doublet absorption transition is observed at 589 and 589.6 nanometer. So lambda 1 is supposed to be lambda 1 is supposed to be 589 nanometer and lambda 2 is supposed to be 589.6. Okay, calculate the frequency of each. What do you do? Frequency will be C by lambda 1 and the nu2 will be C by lambda 2. Also, they are asking you the energy difference. So what will you do? E1 is equal to H nu 1. E2 is equal to H nu 2. Substitute the frequency value and subtract E2 minus E1. Is that okay?
Yes, ma'am.
Kanika, clear?
Ma'am, could you hear me?
Yeah, I can hear you. Tell me.
Ma'am, I had a power cut, ma'am, so I had to join again.
Yeah. See, we were discussing this 50th question, Ganika. Look at this problem. The longest wavelength doublet absorption transition. Okay, so there are some transitions corresponding to 589 and 589.6 nanometer. So one of the transition is corresponding to 589 nanometer. Another transition is corresponding to 589.6 nanometer. Now they are asking you to calculate the frequency of each transition. You are given the wavelength value, lambda 1 and lambda 2. So can you not correspondingly find out what is frequency 1 and frequency 2? We know the relationship, no? C is equal to nu lambda.
Yes, ma'am.
Further, they are saying calculate the energy difference between the two excited states. So one of the excited state is actually one of the excited state corresponds to absorption of the wavelength 589 nanometer. Okay, some energy will be absorbed, from this to this. Another one is moving from this probably to higher level or lower level to lower level, and the wavelength for that particular thing is what is lambda 2 is equal to 589.6 nanometer. Higher the wavelength, lower the energy, remember. So lower the energy, lower the position of the electron in the excited state, right?
Yes, ma'am.
So what is happening now? You have got the lambda 1 and lambda 2. We know that C is equal to nu lambda. If you know the lambda, if you know the C, can you not find out the frequency value? Frequency 1 and frequency 2. Using lambda 1,
Yes,
lambda
ma'am.
2, you can calculate the frequency 1, frequency 2. Also, if you know the frequency, they're asking you the energy difference. So what do you have to do? For the new one type of transition, the corresponding energy is even. for the nu2 type of electromagnetic radiation absorbed, E2 is the energy. They are asking you to find out the difference in the energies of the two states. So E2 minus E1 will give you the answer. Is it okay?
Yes, ma'am.
So these questions are done, right? So well, let us just summarize. What do we now have? We have completed a lot many questions, correct? Whatever
Yes, ma'am.
I'm circling, I'm trying to. These questions, I feel you will not have a problem. How many neutrons and protons are there in the following? These are the first lesson based questions. Find the total number of and total mass of the protons in 34 milligrams of ammonia at STP. Isn't it mole concept?
Yes, ma'am.
Yeah. Ammonia is 17 grams. NH3's molar mass is 17. 17 grams. The talk is about the total number and total mass of the protons. Total number of protons. So nitrogen has 7. Hydrogen will have 1. So 3 times 1. That means a total of 10 in one molecule. 17 gram is the mass of 1 mole. That means we will have Avogadro number into 10 protons, correct? In 17 grams. In 17 grams, there are first of all Avogadro molecules. Each molecule has got 10 protons. So total number of protons will become Avogadro into 10, correct?
10. Yes, ma'am.
Okay. If 17 grams has got Avogadro into 10 protons, then 34 milligrams will have how much? Isn't it a direct relationship? The question is, they're asking you to calculate the total number of protons in 34 milligrams of ammonia. Is it okay? Nitrogen's atomic number is 7, hydrogen is 1. So 7 plus 3 plus 1, which is 3 into 1, which is 10. This is in one molecule. So 1 mole, which weighs 17 grams, right? How 17 grams? Nitrogen's atomic mass is 14. Hydrogen is 3 times 1, so 17 grams. 1 mole, which weighs 17 grams, will have Avogadro molecules. So 17 grams of ammonia will have Avogadro times 10 protons, because one molecule has 10. So Avogadro molecules will have into 10 times the protons. If this is the relationship, then 34 milligrams, 34 into 10 to the power minus 3 grams, will have how many? Isn't it easy, children?
Yes, ma'am.
By 17. Okay. Then look at the mass of the proton. Okay. And multiply that to the number that will give you the mass of the proton. Is that fine?
Yes, ma'am.
Okay. We are just tallying up that, okay, we have done these questions. And what is the mass of the proton? The mass of the proton is same as the mass of the neutron. 1.675 into 10 to the power minus 27. Your electron alone is 1 by 2000th of a proton, which is 9.1 into 10 to the power minus 31 kilogram. What happened? Who is leaving and joining? Ganeka. Having some issues with the...
No,
Ma'am,
no, earlier I joined the
Can't hear
no,
you
this time
clearly.
it was.
Sorry?
Ma'am, this time it was me, ma'am. I'm very sorry.
Okay.
I
No
think
issues,
they are
sir.
also
See,
listening.
Lila, I'm just worried about you getting not proper connection. Any lack of clarity from my side?
No, ma'am. It's just this laptop.
Okay. Okay, so we'll just
Not have anything.
continue and see whether we have left anything. Will this be a problem, children? 2.3?
No, ma'am.
No.
Which one are the homework?
No.
I'm just checking whether we have to do any more questions from the concept that we have finished so far.
Right, yes, ma'am.
Yes, Maganika, tell me. You were saying something?
No, I told you already.
Okay. Your voice is muffled actually for us, I believe. Yes, Shri?
Yes, ma'am. It's a
Her
little
voice, yeah, muffled. Okay. 2.4 also should not be a problem, right? Given the atomic number, given the mass number, you can use the periodic table also and find out the element which is, okay, what is the symbol of it. These questions we have already done 2.5, 6, 7, 8. Last time we did this, that we cannot use the Bohr's model for sodium atom because it is not one electron system. So we directly used E is equal to Hc by lambda and calculated the E. Okay, so these 13th question, 14th, 2, I think up to this we have done. Calculate the wavelength. Up to 19th we have done. Correct me, Ma, if I'm wrong.
Yes, ma'am.
Okay, so we are left out with some more questions here. And in the later part, we have done these things, I think. 28th, 29th, 30th, we have
Yes,
done
ma'am.
related to quantum numbers. This one, we have not done this. It's pending. We have done this. We have done, I gave these questions as homework. And you said that you could do everything. Okay. These up to 50th over. Then 51, 52, 53, and 54 we did under the photoelectric effect. Even 55, if I have not given, you can go ahead. This, you can do. Okay, you can do 55, 56. Same as the Bohr's model. Bohr's model you can use. Okay, again, read the question and see whether it is really Bohr's model. Emission, transition. Okay, in the Paschen series. So everything points to the Bohr's model, na? Atomic spectrum and the Bohr's model, right?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. Paschen series ends at the orbit n is equal to 3, starts from n and can be represented with. So the same equation in modified form. Don't wonder what it is. I'll tell you what it is. We know the Bohr's model. What is that? 1 by, okay, E is equal to so the Bohr's model equation says what? See, don't wonder about what this expression is something new and all. We know del E is equal to 2.18 into 10 to the power minus 80, 2.18 into 10 to the power minus 80, 1 by n1 square minus 1 by n2 square into z square. Okay, if it is for hydrogen atom, the z can be removed and we can put it as 1 and joule per atom is the unit. Okay, now this seems to be frequency. This seems to be frequency. That means what? We know del E is equal to h nu na. Right.
Yes, ma'am.
So if you take the del E and divide it by h, will you not be left out? So can we divide the whole thing by h and call this quantity del E by h to be the frequency?
Yes, ma'am.
So 2.18 into 10 to the power minus 18 by h will also be the frequency. And that value is what is 3.29 into 10 to the power 15. I'll just show you. 2.18. It's 2.18 divided by 6.626. See, 0.329. So when you adjust the decimal, it will become the same. 0.329. It's 0.329 into 10 to the power minus 18. In the denominator, you had 10 to the power minus 34. Okay. So you bring it up and that becomes 10 to the power plus 34. Right. So this will be how much totally? It will be 16 plus 16. Okay. And you shift the decimal and this would become 3.29 into 10 to the power 50. 1 by n1 square minus 1 by n2 square is equal to the frequency. Don't wonder what this is. You just go back and see what concept it is talking about. Emission transition in Paschen series, etc., etc. Okay. Now, calculate the value of n if the transition is observed at 1285 nanometer. Find the region of the spectrum. Find the region of the spectrum. So, what are they saying? The frequency equation is given as 3.29 into 10 to the power 15, 1 by 3 square minus 1 by n square, such that they want the wavelength to be 1285 nanometer. If the wavelength is so much, what will be the corresponding frequency? Frequency will be c by lambda. So can we now write that it is 3 into 10 to the power 8 divided by this 1285 into 10 to the power minus 9? Won't that become your frequency value, children? 3 into 10 to the power 8 divided by 1285. So let us substitute this in the frequency and find out what should be the value of n. Is that clear?
Yes.
Okay. Correspondingly, what will you do? Look at the lambda value. Look at the lambda value. Look at the frequency value. Refer to the electromagnetic spectrum. You had the continuous spectrum part, remember? You had the continuous spectrum.
Yes.
Go and refer to that and find out in which part of the spectrum it will be. So we can quickly 1285 nanometer. Na? So we can refer to it and we can tell which part. One two 85 nanometers.
So in the exam, we're supposed to know.
They won't ask you to memorize, okay? 1285. 1285 into 10 to the power minus 9 meters. Okay, that's its lambda. So where is it? Somewhere can we say here? Worry more about the 10 to the power minus 9, children. It's between 10 to the power minus 8 and 10 to the power minus 9. So somewhere here. So can we say this lies in the X-rays?
Yes, ma'am.
Okay. Okay. Is it clear?
Yes, ma'am.
Okay. Same way, this also, see, they have given you the wavelength values, lambda 1, lambda 2. Name the series to which this transition belongs and the region of spectrum. You try this on your own. Calculate. What you will do? Calculate the wavelength for the emission transition if it starts from the orbit having so much radius. So much radius. Oh, I saw the unit and I went and said it is wavelength. No, it's radius. So what do? I'll write it here itself. What will you do? We know that Rn is equal to An square. Remember? Bohr's radius formula. So now radius is given 1.3225 into 10 to the power minus 9 meters is equal to 52.9 picometers, 10 to the power minus 12 meters, that means, into n square. This will give you one n value. Similarly, go for the second radius. And you say that 211.6 into 10 to the power minus, this is picometer, remember children, minus 12 meter is equal to 52.9 into 10 to the power minus 12 meters into n square. From there, you get the n value again. So describe this and say that it is moving from here to there. That's all. And what do? Lower value will indicate the series to which it belongs, correct?
Yes, ma'am.
So I'll put it this way. Isn't it 1.1322.5 into 10 to the power minus 12? I'm going to shift and calculate. Okay. So the lower value will indicate the series. So 1322.5 divided by 52.9, because 10 to the power minus 12, and that will be cancelled. It's 25. So what will be n value correspondingly, children? What did I do? 1322.5 into 10 to the power minus 12 divided by 52.9 into 10 to the power minus 12 is giving me n square. So this will get cancelled. This is happening to be 25. So what is n value? Can we say 5?
5. Yes, ma'am.
Same way here also you can do. Right? This
Yes.
looks like 2, na? No, it's 4. 10 to the power minus 12 minus 12. This looks like 4 times. So n square is equal to 4. So can we say n is equal to 2?
Yes, ma'am.
That means it is n1 is equal to 2 and n2 is equal to 5, correct? n1
Yes,
is
ma'am.
equal to 2 and n2 is equal to 5. So what is the name of the series? Series. Anything which ends at n is equal to 2 will be called as what?
Balmer series.
Balmer series. So this is part of the Balmer series. Is it okay?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Have you taken this? This
Just a
was
second,
question
ma'am.
number 56. Question number 56.
Just a minute, ma'am.
Yes, ma. Yes. Sweet.
Yes, ma'am. I've got it.
Okay. Then we have already done 60-second question. Okay. Arranging the various electrons in increasing order of energy. We have done already this question. We have not touched these questions. So we will do it after we discuss the further concepts. Okay. So far, we have done, we can classify the numericals into the wave nature of light. C is equal to nu lambda. Okay, number 1. It can be related to time period. It can be related to wave number, all that. Okay, because what is wave number? 1 by lambda. What is time period? 1 by frequency. Okay, then second part, we did photoelectric effect numericals. Right, E naught or E is equal to E naught plus half mv square. Work function plus the kinetic energy. So we had problems related to that. Then we did Bohr's model. Okay, in which we had a number of expressions. 1 by lambda is equal to 1.09677 into 10 to the power 7, 1 by n1 square minus 1 by n2 square, and so on. Similarly, del E expression, similarly, radius equation. Are you able to understand? We have done the problems related to all these concepts. And some miscellaneous, like the diameter of the atom is given, how many atoms should be arranged. Okay, we also have done the Planck's quantization model where it says E is equal to NH nu or NHC by lambda. So if we are given the total energy and energy of a single photon, then we could calculate how many photons would make so much energy. Okay. So we have done
Yes.
problems related to these topics. Now we are going to the lesson to continue. Now, so far, did we discuss the drawbacks of Bohr's model, children?
Yes, ma'am.
Drawbacks we did
Yes.
discuss.
We're supposed to do Heisenberg
Yes.
uncertainty level.
Okay. What about de Broglie equation? That's done. Na?
Yes.
De Broglie equation, de Broglie wavelength. We have done this. Have we?
Yes.
Have we done this? Okay, done. Okay. In that case, there are some questions related to that. I think last week I remember hockey ball, etc. We were doing some sense. Okay. Now, coming to Heisenberg uncertainty principle. Okay. Now, first thing first, in the beginning of the lesson, we understood that light has got the dual nature. Okay. So we were talking about the particle nature and wave nature. The particle nature of the light helped us to understand the spectra also, and which helped in turn to arrive at the Bohr's model, right? The understanding of the hydrogen spectrum and the Bohr's model can be made only if you treat light as particle. Okay. Now there were some problems with the Bohr's model, right? What were the problems? It could not explain the chemical bonding. Okay, it could not explain the splitting of the spectral lines in the presence of magnetic field and electric field. Okay, it could not explain the spectrum of atoms anybody other than hydrogen. It could explain hydrogen spectrum, but nothing other than hydrogen. So these were some of the limitations. Okay. In the meantime, around 15 years, around 10 to 12 years, we can say, some more developments took place. What were the developments? The developments were like light should be treated to be having dual nature, even matter should be treated to be having the dual nature. That means whether an object is big or small, it is having wave like character. Whether an object is large or small, it will have a wave character. But if it is large, the wave character is negligible. But if it is very small, like an electron or a dust particle, then the wave character is prominent and the wavelength exhibited by it will be equal to h upon mv. This was given by de Broglie. Some people will say de Broglie equation, or I would say de Broglie equation. Okay. After this, what happened? So it took there were around 10 to 12 years of development. Okay. So Bohr's model was there, but with a lot of objections. And some more developments happened. First development was the wave character of the matter. The second most important was, by this time, Heisenberg, another German physicist named Heisenberg, right, uh, proposed a theory saying that for an particle which is having very, 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 very small mass, the uncertainty associated with the measurement of momentum of it and the position of it is too high. There is if you look at the title itself, it says Heisenberg uncertainty principle. Uncertain. There are a lot of things which are uncertain about electron. What are the things which are uncertain about the electron? Assume that an electron is there in the first shell. Okay, here afterwards, I won't say it is revolving. According to Bohr's model, the electron is revolving, correct? In Rutherford's model, what is the difference between Rutherford's model? In Rutherford's model, Rutherford said that the electron is moving in a circular orbit. Bohr said that the electron is revolving in an energy level. It is revolving in an energy level. And as long as it is moving in the energy level at a radius of Rn given by 52.9 picometers, that is an square picometers distance, it won't lose or gain energy. But if it is provided energy equal to the difference between the two energy levels, then the electron would move to the higher level. Are you able to understand? Rutherford did not talk about shells. He talked about circular orbits. That's it. Whereas Bohr could say that the electrons are revolving on certain allowed energy levels called as shells, namely K, L, M, and shell. As long as it is there, no energy loss, no energy gain. But if electromagnetic radiation is good enough to supply it energy required to go to the higher level, it will go. And when it comes back, it is emitting the same radiation, which forms the emission spectrum. All this was okay. But now, Heisenberg uncertainty principle says that the electron is too small, 9.1 into 10 to the power minus 31 kilogram. It is so small that, how do you measure the position of an object? Say a bus is here. Okay, the bus shot up, right, with some speed. It is traveling constantly. And after, say, 30 minutes, you would calculate the distance and say that it would have gone to some place which is 20 kilometers away from the point of origin, correct? Because its average speed is so much, so it would have traveled 20 kilometers in this 30 minutes. Are you not using the classical laws of motion, children? V is equal to U plus AT, S is equal to UT plus half AT square. V square is equal to U square plus 2AS. Are you not going to find out the position of this bus using these laws, children? These equations?
Yes, ma'am.
Yeah. But you try to apply it to an electron, what would happen?
It'll be too small.
Too small and too uncertain. I'll just give you a perspective. Have you observed Tyndall effect at your homes? Tyndall effect. When a beam of light enters your room, you see the
Yes,
particles
ma'am.
of dust moving here and there. Are you able
Yes,
to
ma'am.
follow their path? Are you able to predict their path?
No, ma'am.
No. And why are you not able to do so? The forces acting on such a small particle is like something like air. Okay, the particle never moves in a straight line. It moves here, somebody hits it. It moves there, somebody hits it. It moves here, somebody hits it. Or they may have inter particle collision. They move randomly, right? They move randomly.
Yes, ma'am.
So, being so small is a disadvantage with the dust particle. It does not follow a trajectory. It does not follow a trajectory. If you are going to hit a hockey ball with a hockey stick, we know that the ball is going to fly like this and it will be landing there, right? But can you predict like that about a dust particle? Yeah, it is
No,
falling
ma'am.
down. It will fall down. Does it happen? The dust
No,
particles
ma'am.
never settle. They keep moving. So it's very uncertain. Similarly, the electron being so tiny in nature, there is lot of uncertainty. We are unable to. Electron is certain about it. Okay, does God exist or not? I believe yes, God is existing. Where is he? I don't know, but he knows where he is. Understood?
Yes, ma'am.
We are unable to tell. We are unable to tell about an electron. It's highly uncertain where the electron is at this moment. Supposing I'm giving you a hydrogen atom. Okay, I'm giving you one hydrogen atom and I'm asking you, where is its electron? You cannot identify the position and with what velocity it is moving with certainty in an atom of hydrogen, because the electron is so tiny. Okay, so tiny that it is so random. It is certain. Electron is certain about itself. But as an onlooker, I am observing it and I cannot find out where the electron is at this time, moving at what velocity. So it is not the problem with the electron. Electron is tiny is the problem. But the most of the problem is with us. We are unable to locate or predict the motion of the electron. there is too much of uncertainty associated with the measurement of electrons' velocity and electrons' position. Did you understand the statement?
Yes, ma'am.
And if we are so uncertain, then how can Bohr say that the electron is found at a distance of Rn 52.9 n square? Is it right on the part of Bohr to claim that electron is located here?
It won't be exact.
Are you able to understand the issue?
Yes,
Bohr,
ma'am.
Bohr proposed that an electron is present at this distance. It may be present at 52.9 into 1 square picometer, 52.9 picometer, or it can be 52.9 into 4 picometer if it is in the second shell, or it will be 52.9 into 9 picometer. Okay, 3 square, 4 square, 5 square. So Bohr could say where the electron is. But the latest theory says that it is impossible to determine the exact position and exact velocity of an electron simultaneously. If you cannot do so, how can you say that the electron is located here? Say your father left the house for his office, okay? Okay, he's going by a car. Right? At 9 a.m., he left the home. Okay. And you know that he is going to take around 1 hour and 10 minutes. So you know that at 10 a.m., he will be at the office, correct? You are able to project his position. There is lot of
Yes, ma'am.
certainty. But what about an electron? Electron is too tiny. So after 1 second, where the electron is, we cannot say with certainty. Then how is Bohr's proposal correct? Bohr is predicting that the electron is located at this distance from the nucleus, or at this distance from the nucleus, or at this distance from the nucleus. So the entire Bohr's theory falls flat with the acceptance of Heisenberg uncertainty principle. Understood?
Yes, ma'am.
Okay. So what is the mathematical expression for the Heisenberg uncertainty principle? He says that the uncertainty, what is this del x and del p? I'll tell you. These are not uh, the position and all. Supposing I'm asking you to find the length of this line. What is the length of this line? What will you do? You will bring a scale and you will put the scale making the zero coincide with this point and measure. Correct? Assume that this ends between 7.7 and 7.8. Okay? It lies between the two. Okay? So can we say that it is or around that point, 7.7, but not exactly coinciding? So can I say it is 7.7 centimeter plus or minus 0.5 centimeter? The length
Yes.
of this line, because my scale is not exactly correct. So it is around 7.7, maybe plus 5 more or plus 5 less. This more or less plus 5 is called as the uncertainty. We are sure that it is 7.7. It's more or less by a small value called 0.5. This is uncertainty. I told no, your father is leaving the house and he is supposed to reach the office by 10 a.m. So can I say that he may be plus or minus 15 minutes either early or late to his office? Early because probably the traffic is not there, and late probably because there was a lot of traffic. So what is the uncertainty in the measurement of the time at which he will reach? It's the 15 minutes. Got it?
Yes, ma'am.
This, similarly, when an electron is moving, where is it? From the starting point, where is it? it should be at a distance of, let us say, some 6 centimeters. Okay. Plus or minus del x. Plus or minus del x. So del x is uncertainty associated with the measurement of position. It's not the position itself. Uncertainty associated with the position of electron. For example, if I'm giving you a bag full of, say, cashews, a packet full of cashews, and I'm asking you to look at it and I'm asking you how many cashews are there. You will say, ma'am, it may be 100 plus or minus 10 pieces. This is the uncertainty. Understood? This is
Yes,
your
ma'am.
del x. So similarly, the position, the theory says, the Heisenberg uncertainty theory proposes that the uncertainty associated with the position of the electron is del x. The uncertainty along with the measurement of velocity is del v. Obviously, it's so tiny. You cannot measure where it is located at a given point. And at the same time, at what velocity it is traveling, you cannot determine. So supposing, okay, you took some efforts and measured the position with somewhat accuracy. So this del x is very small. Okay, the uncertainty is very small. Let us apply. The Heisenberg uncertainty principle says that the del x multiplied to the del p, uncertainty in the position multiplied to uncertainty in the momentum, is either equal to or greater than h upon 4 pi. Remember, h is a very small quantity, 6.626 into 10 to the power minus 34. 4 and 22 by 7 or 3.14 will make it even more smaller. But as soon as the particle is an electron, even this uncertainty is large. Say you measured the position of the electron with very little uncertainty. You're almost sure. So the del x value will reduce, no? Supposing you are able to predict your father's arrival more accurately, will it become 10 a.m. plus or minus 5 or plus or minus 20? Which is more accurate prediction?
Plus or
Plus
minus
or minus
5.
5.
Okay, so you are able to reduce del x, correct? If you
Yes,
are
ma'am.
able to reduce del x, take it to the denominator. A very small del x means what will happen to the momentum? Uncertainty in the momentum
Increase.
increases. So even if you have painstakingly found out the position of an electron with less uncertainty, eventually your uncertainty in the momentum will be too large. That means Heisenberg uncertainty principle says that one cannot determine the exact position and velocity of an electron simultaneously with absolute certainty. If you are so uncertain, if the theory says you cannot predict, then how is Bohr able to propose that the electron is at this orbit? And what were the reasons? Electron was treated as a particle in the Bohr's period, whereas now the electron will be treated as a wave. Henceforth, electron will also be treated as a wave. Got it?
Yes, ma'am.
Wave nature of a subatomic particle cannot be neglected. There is too much of uncertainty associated with subatomic particles. So you cannot treat a subatomic particle just as a particle, just as how Bohr treated. Instead, you have to start treating it as having both wave and particle nature. Are we clear?
Yes, ma'am.
Okay.
Yes.
And converse is also true. If you have identified what is the expression del x times the del p. What is del p? Del p is m times del v. So you found out mass is not uncertain. Mass is fixed. 9.1 into 10 to the power minus 31 is fixed. Okay.
Yes, ma'am.
So if you have found out the del v certainly, that means the uncertainty reduces plus or minus 3, let us say. If this is so small, then the del x depending upon the del v will become large. Del x becomes, if the del v is small, del x is large. So this was the point at which the Bohr's model failed. Are we clear?
Ma'am, so they're
Are we
like
clear?
inversely proportional or something?
Yeah, they are inversely proportional. If the
Yes, ma'am.
uncertainty in the position is low, uncertainty in the velocity is high,
Yes, ma'am.
such that the product of the two is always greater than or equal to h upon 4 pi. So you are modifying this equation. Del x times del p is equal to or greater than h upon 4 pi. You can expand this del p and say it is m times del v. Take the mass and put it over here. That is another form of the expression of the Heisenberg uncertainty principle.
Yes, ma'am.
Okay. And why so uncertain? I'll tell you. Why so uncertain? Supposing I want to find out the position of an electron. Okay. I want to know where Shri is now. Should I not look at Shri? If your mother wants to spot in which room Shri is sitting and studying, she must look at you. Am I right? Your mom should look at Shri, na? She should
Yes,
look
ma'am.
at. And to look at Shri, light of certain light packets carrying h nu amount of energy should fall on her and should be reflected back to her mom's eyes. She will frame an image of her sitting on the study table and studying. Now imagine her mom is trying to look at an electron. Light of h nu energy as a packet is coming and hitting. What will happen to the electron?
It'll get disturbed, no?
Yeah, that's all. When fell on Shri, Shri is not disturbed by the light. Instead, she reflects this light to her mom's eyes. But if in the place of Shri it is an electron, a parcel as big as h nu amount of energy containing particle falls on it, thinking that it will reflect, then it would definitely reflect. But by the time the electron would have been kicked out of its position and it would be somewhere else. By the time mom perceives the idea that electron is here, electron actually went somewhere else. Understood?
Yes, ma'am.
So it's the problem with the size of the electron. It's the problem with the electron. It's not the problem with us. It's the problem with the size of electron. Also, it is problem on our side that we have not been able to maybe invent a device or invent a method through which we can look at an electron with preciseness. Is it okay?
Yes, ma'am.
Okay. So the significance of uncertainty principle is that it could decisively say that Bohr's model is incorrect. There is no definite path or trajectory of an electron. There is no, we were talking about Bohr's model saying that electrons are revolving in certain allowed energy levels. Okay. But Heisenberg says nothing like that. Electrons are revolving? No. Electrons are having a trajectory? No. So where are they actually? Where are they? How are they? We have understood the electronic configuration, correct? We have understood
Yes,
the
ma'am.
electronic configuration. So where exactly is this electron? I'll tell you. I'm going to think that I'm going to click a picture of, I'm going to take a picture of electron in hydrogen atom. And definitely if I'm going to take a video, I'm going to think, okay, definitely I can't take a video. Just now I told you that we cannot picturize, because to picture or to see something, the light should fall on the object and should reflect back to me. That's not going to happen. But I'm going to imagine that I'm able to look at an electron. So if I'm going to view the video of an electron is no way traveling in a circular orbit like this smoothly. It's not happening. Okay, let me take the picture of the electron. Where is the electron? This is the nucleus of hydrogen atom. Where is the electron? One picture says the electron is here. The next picture will say that the electron is here. The next picture says electron is here, 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 here. So I'm taking infinite number of pictures, and each time the electron is found to be in a different position than the previous. But the overall dots that I could collect looks to be spherical, not circular. Please understand. On a board, I can only draw two-dimensional structure. It's actually a sphere. So when I try to draw the line to cover the maximum number of points, what I get is a spherical shape. And that happens to be the shape of 1s, remember.
Yes, ma'am.
Okay. When I take the electron of nitrogen, nitrogen is 1s2, 2s2, 2p6. So I'm going to, 2p3, nitrogen is 7. So I'm going to look at the 2p electrons. And what was the shape of 2p, you remember? It was px, remember, py and pz.
Yes, ma'am.
Okay. And I told you, I was showing you one picture from the website. This is the nucleus. This is the region of 1s. It's not the shell, it's the region of 1s. This is the region of 2s, correct? And the
Yes, ma'am.
2p, where is the 2p? 2px, 2py, and 2pz. Do you think the electron is revolving in this direction, children? Taking the path of an H? No. No. The trajectory of an electron cannot be predicted. Just now we said, right? So I'm going to remove the 1s and 2s for the simplicity. Fine. I'm going to remove. What is this actually? This is a 2px. How did we get that? Again, I'm going to take the picture of this 2p electron, this electron, infinite times. I'm going to take the electron's picture. Again, I can only imagine that I'm taking picture of this electron infinite times. Now, every time I take the electron's picture, it is found somewhere like this. It is found to be somewhere in this region. And if I draw lines to incorporate or cover up the area, it looks like a dumbbell. Are you able to understand?
Yes,
Do
ma'am.
you think the electron will be inside the nucleus at some point? If it is revolving, then at some point of time it should cross the nucleus, penetrate the nucleus. Do you think electron can penetrate the nucleus?
No, ma'am.
No way. So what is projected here is only the picture of where the electron could be. If you assemble the points and draw a line covering up most of it, then you get the dumbbell shape. And that's why the shapes that we draw are also called as boundary surface diagram. The shapes that we draw, the S is spherical, P is dumbbell. These are all boundary surface diagrams. So first the electron is viewed. Where is it? Oh, here it is. Cover up, draw a line covering most of the points where the electron is found. Once the lines are drawn, what it looks like after covering that area is said to be a dumbbell. So it's said to be boundary surface diagram. Are we clear?
Yes, ma'am.
Okay.
Okay.
So now tell me, is the electron found here? Is the electron found here?
Yes, ma'am.
Okay. You can't say yes, Shri, because
It might
next
be.
moment it might be. So hence, very good. We are going to talk about probability. We cannot talk about electron is going to be found there, found that Rn is equal to 52.9 n square. We can say it's the probability of finding the electron is maximum in this region. The region around the nucleus where the probability of finding the electron is maximum is concluded to be orbital. Remember the word orbital? The ML values were telling us the orbitals. Is
Yes,
it clear?
Ma'am, so it's
Yes, ma'am.
possible for an electron to be a little out of
Yeah,
that
it can be. Okay.
boundary?
Now my question is, what is the probability of, I'm actually, where is your house, Shri, in Chennai?
OMR, ma'am.
Okay. What is the probability of Shri's presence in Anna Nagar? Even at the time when she is speaking to me, what is the probability of Shri being found at Anna Nagar? I can say close to zero, but never zero.
Right, yes, ma'am.
So we are trying to cover, see, that means Shri can be anywhere on this earth, but she's most likely in and around OMR. So Shri
Yes,
can be
ma'am.
found here. Shri can be found here in US, in Australia, maybe in Delhi, maybe in Calcutta, maybe somewhere else. But most likely she is found in and around OMR. So I'm trying to draw a line or draw a shell around the space in which you can be found, and that looks like a sphere. If it looks like a sphere, I'll call it as an S subshell. What is the probability of Shri being found at Delhi? You can't say equal to zero. You will say it is very less. You can't say it is exactly zero. Got it? So
Yes,
there
ma'am.
is, you were asking, can
Yes,
there be
ma'am.
some points outside? Yes, it can be outside. But where are you going to be most likely be found? Inside this region. So I'm drawing maybe a shell-like structure around this. On a paper, it looks like a circle to encase the region where the probability of finding you is more. If that looks like a sphere, it is S. If it looks like a dumbbell, it is P. Got it?
Yes, ma'am.
Okay.
Yes,
So
ma'am.
what I want you people to do is, we have the numericals to be done. These numericals are quite simple. You please try. Okay. For example, let me take one and give you some homework. Okay. Or I'll put it this way. I feel you, after traveling this much, you will be able to do some example questions and apply it in the unknown cases, children, both of you.
Yes, ma'am.
Yes,
Ganika?
ma'am.
Okay, Ganika, then do these problems. 2.15, 2.16, read from the text. It's about the uncertainty in the position. It's about the uncertainty involved in the measurement of velocity. So do these. Okay, read this also. We have discussed this, that the electron was never treated as a wave in Bohr's period. So that led to the failure of the Bohr's model. So you can go through this also. I want you to start reading from the de Broglie wavelength, Heisenberg uncertainty principle, and the reasons for the failure. Up to this, please go through. Okay, do
Yes,
those two sums, and I'll mark a few more questions from your exercise as homework. We are almost coming to the end of this lesson. Okay. See, is this not de Broglie wavelength? I'll put it as de Broglie wavelength. V lambda. Okay. Again, I'm asking you also to interpret the hockey ball wavelength associated with this velocity. A hockey ball having wave-like character. Understood? Is this again straight away de Broglie wavelength? Okay. So 60 and 59. Okay. Then 57. Read the context. Dual behavior of matter proposed by de Broglie led to the discovery of electron microscope, often used for high magnified images of the biological molecules and other type of material. For your information, if the velocity of the electron in this microscope is so much, calculate the wavelength, de Broglie wavelength. So this is de Broglie wavelength question. Okay. Similar to electron diffraction, neutron diffraction microscopes are also used for determination. If the wavelength used here is so much, calculate the velocity associated. So this is also in the same context. Na? So this also must be de Broglie wavelength. Because neutron is treated as a particle having some wave character. So take these as homework 57, 58, 59, 60. Some more questions. Some more questions are there. I think that's all. I think that's all.
Mom, so I've noted these 4 questions and the third and fourth one. Just
Look at this. Calculate the wavelength of electron moving with a velocity of 2.21. The mass of an electron, kinetic energy. Is it related to photoelectric emission? Because kinetic energy we saw in photoelectric emission. So is the story talking about an electron when light of a suitable frequency falls on a metal, electrons are ejected with so and so kinetic energy? Does this sound like that story? Or is it about de Broglie wavelength? Electron with so much of mass, calculate its wavelength. Is it not for an electron you are calculating the wavelength character of it? Are these two not related to de Broglie?
Yes, ma'am.
yes.
Okay. So 20, 21, and in the last page, I think I gave you 4 sums. Correct? 57, 58, 59, 60. Yes, Shri, you were asking. There are some example questions in your text. Go through that and then come and do these problems. If you have any doubts, next class I'll clarify.
Yes, ma'am.
Okay? Yes, ma, Shri, something you were saying.
No, ma'am. I was just noting down a few questions. I wanted to know if that's it.
Is it okay, Ganeka?
Yes, ma'am.
Okay. Right. So I'll see you again on today's Tuesday, so Thursday. Okay?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay,
ma'am.
bye.
Thank you, ma'am.
Bye.